So since this section involves weak acids and weak bases and their pHs, you need to remember how acids interact with water. And again, this was in the last section, but we're also going to go ahead and name them as Ka or Kb. I'm writing the water more as like the Lewis structure so you can see the lone pairs. So in this first case, HNO2, AQ, that's a weak acid, and I know that because it's not on the list of weak acids. So it has an H in the front, and it's not on the list of strong acids. HNO3 is strong, but not HNO2. I know this is an acid because it's an H as part of a COOH, and we already talked about in the electrolyte section. It's a weak acid. And then this one, because it has an N in it with these H's in here, that's to be recognized as a base. So we have an acid, and base. So there's just certain places you look for these. Other examples of base might have been like Fe, a strong base would be like NaOH. A lot of the other bases that would normally be like more weak, they actually are going to turn out to be salts. We're going to see them in a different place. So I'm going to focus on what's going on right here. My hydrogen is going to transfer over. That's an acid. It's going to want to give up as H. And so it gives it up as H+. So the H2O becomes H3O plus because it gets an H plus added to it. And the same thing happens right here. This H comes over and makes a bond with the oxygen's extra electrons right there. And then in this one, these hydrogens don't want to move because he's got some lone pairs. The direction that it's going to go is actually this way. And again, it's because it's a nitrogen, and you just have to know that's what happens. So my chemistry is like that. You learn what happens, and then you learn a whole lot more, and you finally figure out why it happened. So in this case, I'm going to end up with, the way I've written it, I'll write it over here, OH minus. And then we can write what's left over. Up here, what's left over is the NO2 minus. What's left over here is going to be CH3COO minus. And then what's left over here is C6H5NH. And since it got an H, it came over as H plus. NH3 plus. Like the H comes without the electron that it bonded with originally in this scenario. It comes over without it. And for phases, AQ, 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 they're all aqueous. Notice this is back and forth though. So for weak acids, it has it's like times 10 to the like negative third to like times 10 to the minus eighth. These are very, very small situations. Like this is much, much less than this. And so our pH it's not like we have a strong acid, because a strong acid would completely break into all those parts. It spends a lot of its time as this, and only some of them, a very small percentage, break apart into this, but it's enough to give us a pH reading, which is crazy. So let's just look right here. Because this is an acid, this would be a Ka, and because that's a base, it's a Kb. So let's take a look at these. Let me zoom out. I've gotten these over here. So again, because it's an acid, base. But there's another way to tell too. If you got the reaction right, if you make H3O plus over here, and this is my favorite way of telling it, then you've got a Ka. Again, an H3O plus, you've got a Ka. If you have an OH, then you have a Kb. All this is set up the same. The whole reason why water isn't in it is because it's considered a pure liquid. There's so much water in there, and then you just add a little bit of acid. So it's pure water. That's the reactant in that case. But this is being added as aqueous HNO2. And it becomes aqueous in the solution. So if you look at all of this should look familiar. It's all products over the original reactants.